there are ways that we can correct these optical aberrations, and some of them are unfortunately expensive, like buying better equipment. Sometimes you don't have that option though, and so usually what you should try to do is stop down the lens. So don't use it wide open all the time, but stop it down. You'll be able to get rid of a lot of the optical aberrations that exist for that lens. Now, lenses are designed, as you know, with a specific image circle in mind. So as light enters the lens, it's focused onto a circle that is cropped basically by the sensor, because the sensor is square. It's not actually a circle. And the very outside edges of this circle will have the most problems, as you've seen, because it's a result of where this light is being focused. It's just more difficult for the outside regions, particularly the corners of a lens. So usually the hardest thing for a lens to do is to be used wide open, which means the lowest F number possible for that lens, and to look at the corners of that particular shot. That is going to be the most stressful for the lens, and sort of one of the best tests for how well corrected that lens is. Now, as soon as you stop down that lens and use something more along the lines of maybe f8 or f11 even, then you will correct for a lot of these issues, because you will be using the sensor portions of the lens, which will be just inherently better and more corrected than the outside portions of that lens. Now, for a digital SLR lens, generally the range that's ideal is about f8 to about f11. You generally don't want to go much higher than that because of a different concept called diffraction that we're going to talk about next. And you generally don't want to go lower than that. Well, if you can get away with it, you don't want to go lower than that, because then you will get these optical aberrations as a result of using a very low F number. So generally with a digital SLR, you should aim for, especially if you need it to be absolutely perfect, you should aim for something around f8 or f11. Now, compact digital cameras, I would say the same, but unfortunately diffraction comes into play much sooner there. So you exchange these optical problems for a softness, and don't worry, I'll explain this more in just a little bit. You exchange one thing for another much more quickly in a compact digital camera. So generally you might need to get away with something like f5.6, maybe f8, but I suspect that on most compact cameras you're going to be diffraction limited in those cases. So stop down. If you have your camera on a tripod, you're taking a landscape shot, for example, just set it to f8. Just do us all a favor, because if you use this lens wide open, unless you really need to on a landscape shot, you might be disappointed in how relatively soft your image looks versus that same lens on at f8 or so. And even the sharpest lenses in the world do benefit quite a bit, or well, I mean, it varies, but they do benefit by stopping down at least a couple of stops. Okay, let's see. I think diffraction is an interesting topic, but I think we should wait 5 minutes before we talk about that. So let's take a 5-minute break. When we come back, we will talk all about diffraction. All right, hello everyone, welcome back. So we did run a little bit late because everyone was curious about my Thanksgiving story, and that's why you should come to lectures, because you get to hear all of my rants off camera that I also happen to mention. And so, but with that said, we do need to talk about some of the interesting stuff as well that's not related to my holiday plans. That deals specifically with diffraction. And so diffraction is the thing that I've been talking about for a long time, and this goes all the way back to lecture 1 when I took the photo with the pinhole lens, and I posed the question, why is this not sharp? Why is it fuzzy if everything in the image is supposed to be in focus? And the reason is due to this optical phenomenon called diffraction. So those of you that have a good memory and remember your high school physics might remember a couple of experiments that deal with something that looks like this. So usually you might see something like, so us younger folks have had the luxury of using like lasers, but I know that even in earlier high school programs they would use like large water tanks to show off this particular thing. And so all of these things are related because they all deal with basically waves. And so as you remember, light can operate not only, or has characteristics of not only a particle because of the photons, but also waves. And so it's this waves aspect that we're focusing in on right now. And what happens very generally is that we have a set of waves that are coming in, and it hits some obstruction that has a narrow slit in it. And so as you can imagine, this is analogous of a lens that has small aperture within it. And so as the waves pass through this slit, they actually basically wrap around the edge and vary their distances to the other side. But because they vary in distances ever so slightly, we get these weird patterns where sometimes the waves get out of phase and they basically cancel each other out. And there's some portions which become in phase and can, not multiply, but they are as strong as they were before the slit itself. So we see that after this wave has entered through this slit, we get through the center the same wave, but then as we progress outside of this particular portion, we get alternating aspects. So it gets a little bit, there's not as much of a wave right here, it's softer. Then there's another wave right here, and then there's no wave right there. And just to put this into motion, we can see this in a ripple tank. So this is a very similar thing. You will see something that looks almost exactly the same as that still image that I showed you. It's just going to be not quite as high in resolution, so it's harder to see each of these aspects of in phase and out of phase for a particular wave. Now let's see. Okay, so here we can see that there's a variety of, there's some equipment that they use to show us this particular thing, including some light equipment and mirrors and projection screens and all sorts of stuff. Then of course they also have to have a ripple tank as well, where they have a slit right here, and they have some device that actually generates waves in this water. Remember that this is applicable because waves in the water are just like because light operates as a wave, we can use the waves on the surface of the water as an analogy. So we can see that we have this slit here, and the waves propagate out. They sort of they fan out from the center of that slit. So the same thing happens in light. So as the light comes in through this slit, it doesn't just come straight down to the sensor, it also sort of bends and fans out a little bit as well. So the smaller the aperture slit here, the more this is going to become a problem. And in fact, just go back here, what this actually looks like with a point source of light that's poking through a very small slit in say this piece of paper or this wall, is that we have the point in the middle and then these concentric circles, these donuts that go outward from that circle in the center. Now, I would be very surprised if your digital sensor had enough megapixels in it to actually see this exact pattern. But imagine what would happen if you were expecting this one circle to be right in one pixel, right here. And then, of course, you have neighboring pixels. What would this circle look like if you had pixels that were about as large as this center circle right there? So you would see that one center pixel is bright red. But what about these neighboring ones? You'd see they would be just slightly red, right? You wouldn't see this detail because we're talking about pixel level here, but you would see that there is some noticeable amount of red. And so if you actually make the slit smaller, the size of this concentric circle, or this donut shape, will increase. You'll cover more pixels. So what happens then? So you have this red that's supposed to be covering one pixel is now covering multiple pixels. Let's say these 9 that are surrounding it, and it just becomes fuzzy, becomes out of focus. And that's, well, not out of focus, that's incorrect, but it looks out of focus, it looks fuzzy. And that's exactly what can happen when we are dealing with this. So let's say that we take a photo at an aperture of f5.6, which is still relatively large of an f number. Then we stop down to a very small f45. I don't recommend this at all for digital, but you get to see exactly what happens. We destroy a lot of the detail because of this diffraction problem. It just becomes soft. It wraps around this narrow slit that happens to be inside of our lens, and it causes this weird pattern to emerge that you don't see. You don't see that specific wave pattern, but the result is this fuzziness that can happen in your image. Now, because, as you know, pixels vary in size from one sensor to another, so some sensors have very, very small pixels, whereas other sensors have large pixels. Different digital cameras will actually be impacted by diffraction at different f numbers. Okay, because remember that diffraction is going to happen basically anywhere that light passes through like an aperture. But the larger the pixels that we have, the less likely we are to capture the problem, the surrounding concentric circles around that disk. So if we have smaller pixels, like we do in, say, digital cameras, then we're more, or rather compact digital cameras, more specifically, then you're going to start to see diffraction much sooner. And this is one reason that adding more megapixels into already burdened compact digital cameras, and even digital SLRs these days, which are now growing ever so high in their megapixel counts, we're seeing this diffraction problem sooner and sooner and sooner. So just to give you an idea, so we've talked about, or I think we've referenced this particular website at least once before, and I want to do it again because they have a very, very good tool online that not only talks about the same sort of thing, but it also has this neat little diagram here that we can use to try to determine how diffraction will impact us. So it has here a list of f numbers, or rather apertures, and some cameras and associated pixel sizes. So if we actually take a look at some of the pixel sizes, and keep in mind that these are old cameras, so these pixel sizes are larger than they are now. This is an old Canon 1D, which is probably, I don't know, 8 years old now. It's pretty old at this point. You can see that the pixel, these dotted lines here, is actually pretty large. So I'll just keep going down. 1DS, okay, it's smaller, all the way down to a Canon PowerShot, which is a small compact digital camera. You can see how small the pixels are on this particular sensor. Now, we can see that if I modify, let's go back to the 1D here, I can modify the aperture. So the larger the aperture, the less likely I am to have this diffraction problem, because the smaller the slit, the more this is going to be a problem. So if I go from f2 on a particular lens all the way up to f32 on a Canon 1D, you can see how that what used to be a point has now become not out of focus but blurry due to diffraction. And so this one point now covers these 9 pixels, and it's going to look soft and blurry within the image itself. Now I'm just going to go down to a pretty reasonable f8 in this case on a Canon 1D. And then I'm just going to start going down the list of cameras to make the pixels smaller so that you can see, even though I'm dealing with the same size of the aperture, and this is somewhat misleading because normally when we shrink the camera sensor size, what do we also have to do to the lens? For the same field of view, we have to shrink the focal length of the lens, which means because the aperture, the f number is a ratio, we're also shrinking the size of the aperture as well, so the size of the hole when we're talking about this. So f8 in a Canon PowerShot G6 is probably already going to be much smaller than the aperture of a much larger camera that has a much larger lens. Okay? If that doesn't make sense, then review some of the earlier lectures. But I think here they're assuming that the aperture is going to be for the same lens, so that it will generate the same pixels. So assume that we're using the same lens for each of these pixels. Okay, all of that technical detail said, we start making the pixels smaller and smaller and smaller, and we can see that now, whereas before we had no problem due to diffraction at f8, now a compact digital camera has this same problem that we had at much higher f number for a larger sensor. Or rather, and more specifically, a larger sensor that also happens to have larger pixels. So as we increase the megapixel count in these, we're going to have these problems. As we decrease the size of the sensors, we're going to have this problem. As we decrease the size of the lens itself, and therefore make the size of the aperture smaller, we're going to have this problem. So we're working against all of these problems, and modern digital cameras, digital SLRs, unfortunately from Nikon, because Nikon is now, or no, not Nikon, Canon seems to be getting into this really kind of stupid idea of increasing their megapixels ever so frequently in their digital SLRs, whereas Nikon, thank God for them, are keeping their megapixels somewhat low, which means that we're not running into this problem because the pixels are the same size from camera to camera. But on Canon cameras, if you've upgraded to one of the newer like 50Ds or the 70s, the pixel size is so small that you're getting diffraction limited at about f8 or f11, whereas before you could have gotten away with f16 with the very same lens. And in fact, I've started using a 7D, and that's exactly what's happened, is that I've noticed that with these lenses I can't go above f8, and it's frustrating and it's annoying because I sometimes want a greater depth of field. And so you have to exchange sharpness in terms of focus for softness due to diffraction. And so there's no, unfortunately, really good way of fixing this except having, monstrously sized sensors. But then, of course, we have to pay for that in actual cash dollars rather than in any sort of optical way. Okay, anyway, so diffraction is bad for us because it increases the softness of an image without us wanting to do it. So it's counterintuitive because we thought, and we've been told up until all of this time that, increase the f number and you'll get more in focus. You'll get a sharper image than what you had before. And that's true up to a point, but then after you reach this diffraction limit, you will start just getting softer and softer and softer images, and it'll just become increasingly frustrated. So you can use this website. I believe it has a calculator at the bottom where you can actually figure out the f number that you can use without being diffraction limited in your particular camera. And you might be surprised at how relatively low of an f number that actually is for your particular camera. So that's something to keep in mind, and it's something that means that if you want to really get the optimal quality out of your lens and out of your camera, if you have a digital SLR, then I recommend sticking to about f8 to f11. Any smaller of an aperture, you'll start getting diffraction limited pretty much for most digital cameras out there today. And any larger of an aperture, you will start getting optical aberrations from your lens. So if you want the best, f8 to f11 is probably the way to go unless you have a very exceptional lens. Now on compact digital cameras, you will have to experiment, but you may frankly be screwed no matter what you do, because you'll either have optical problems because of low f numbers, or you're going to be diffraction limited due to high f numbers. And so you would have to frankly determine what will be the best, but generally, again, f5.6, f8, even on those would be a good starting point for you to figure out what is the best thing for you to do. Okay, so we talked about a lot of optical artifacts. So we've talked about artifacts involving the lens, artifacts involving properties of light itself, but there's even more artifacts that can exist just because of the nature of digital photography, the nature of the sensor, what we have to do in order to process the images. And we've talked about some of these. So can you name some of these artifacts that we've discussed already? Here's a hint. Let's say you increase the saturation a lot of an image. A lot. It's something like posterization. Oh, good. Okay. So did somebody say that, or did I? Okay, maybe not. So I made you all look smarter, I guess, on camera. Okay, anyways. So posterization is one. We talked about that, where it causes this gradient, what used to be a smooth gradient, have visible steps in it. Another one is, of course, the noise. So the noise that we've seen, that's, it partially has to do with the optical properties as well, but it has a lot to do with the sensor itself. Then blooming, I think I mentioned very briefly. That deals with when you overexpose a particular region. If you really badly overexpose it, the overexposure sort of spills to neighboring pixels, and it makes a bad problem even worse. But there's other things that can happen as well. So if you recall, we have a filter on the very top of the lens. So above the micro lenses, we have this filter called an anti-alias filter. And I mentioned it briefly, but here's a different example of what this thing does. So aliasing is making something more jagged. So if you have something that's aliased, then it's going to have what should be a circle. When you zoom in a little bit, you're going to see these jagged lines because of each of the individual pixels will be visible within it. Now, if you anti-alias something, you're making it a bit softer, and you're making the interface from that solid colored region to a different colored region a bit smoother. So from this yellow to this blue, you can see that now we have a few more colors to deal with, sort of yellow blues, but it's a softer interface. It looks a little bit better. And so this gets rid of the so-called jaggies phenomenon. So typically we have, you see something like this, and people love to call this jaggies, and so that's what we're able to get rid of by anti-aliasing a particular aspect. And so if we have, remember that we are using an anti-alias filter on the front of a digital sensor, and we have to do this because each pixel doesn't actually capture one color. So, well, it doesn't capture all colors. It has to rely on the neighboring pixels to be able to capture or to recombine it later and figure out what that original color was. That can cause weird artifacts when we have very highly alternating patterns. So if it was a lot of lines, as we saw back here in the diffraction one, so if it's a lot of lines and it just so happens that these are different colors and it's alternating from white to black to white to black, take a picture of this, and each of these colors falls on one pixel on your camera because you're sufficiently far away, then it has to guess, and it might get it wrong. It might try to make all of this sort of a gray color like this area just because it's recombining this color incorrectly. And so we have this anti-alias filter to try to make it smoother and eliminate this problem, this high frequency pattern, or this high frequency pattern, same thing, it's twice. So this high frequency problem, eliminate it altogether. Now, there do exist problems that can happen from aliasing. So if we have an image of a building, and this has a very high frequency pattern, as you can see, it goes from the red brick to the white mortar and back and forth very, very quickly. Let's say we shrink this image just ever so slightly and we don't use any anti-aliasing. Okay, so we just shrink the image ever so slightly. The computer has to decide which of these pixels to keep and which ones to throw away. And sometimes if you get it just right, you'll get a pattern that looks like this, where sometimes it has to pick more of the red brick pixels, sometimes it has to pick more of the white mortar pixels, and that's just because there's no finer level of detail. It just can't, it has to throw some detail away and keep other amounts of detail. And so as a result, we get this sort of weird ripple effect that can happen on this brick wall. And this, the result of this is called Moira. And so you might see this, you'll see this especially on compact digital cameras, which might have to have a weak anti-alias filter in order to get some detail out of the particular scene. But so the ones that you might recognize and what might be more familiar are these examples where we have, if you remember, this was some folded over jeans. And so if you know the thread on the jeans alternates from dark blue to a white very, very quickly, and the sensor is incorrectly guessing what the color should be. And more specifically, the camera's computer, the CPU inside, is incorrectly determining what the colors were that made up the original scene. And so we have to use an anti-alias filter to smooth out those details and essentially just get rid of them so that we can just get some higher quality amount of detail than what this provides. And so sometimes you will see some effects like this, Moira and maze patterns. So you still see some Moira. You see the Moira in the colors. You see how it's a patterned orange to blue to orange to blue. That's Moira. Then also you see this maze pattern, which looks just like this maze of pixels. So those are two distinct things that can happen as well. And so the internal processing of the camera can cause this moira to occur and for these maze patterns to appear. And so again, using this anti-alias filter on the front of the sensor helps us eliminate this problem. Now, to try to combat this anti-alias filter, because as you know, using it will make it a bit softer, we can try after the fact to sharpen the image again to try to make it look a bit sharper, a bit crisper, like it might have when you originally took the photo. But the problem with this is that you can definitely overdo the sharpening and you will make it look just plain wrong, just really strange and very unusual. We can get this effect called sharpening halos as a result. So let's say that we have this very heavily anti-aliased circle, as you can see here. Now, this might be nice if this is what you wanted to do, but if you want it to be a sharp, crisp circle, you then need to alias it again. You need to sharpen it somehow. So you might use one of Photoshop's sharpening filters, and actually the one that, and what photographers generally recommend is something called an unsharp mask. And we'll probably talk about that in the, I think we referenced it briefly before, and we'll talk about it again in the upcoming software tools lecture. But generally using this, you can then retrieve some of the sharpness around objects. And basically you can think of it as it finding the edges of something and trying to increase the local contrast. So it's trying to increase the contrast of edges. So it might find an edge interface here, and it might make the inside a little bit darker and the outside a little bit whiter, and that will give the effect of making it look sharper. The problem, though, is that if you overdo it, you will get black on the inside and white on the outside, and it will give this halo effect, which will look fake. It will look bad, and you can see the result of decent sharpening here. So zoomed in, it's not the sharpest thing in the world, but it's still pretty good, as you can see compared to our first image here. Or you can overdo it and just get these weird white halos that surround your circle. And this is generally a bad thing. And cameras, out of the box, will generally apply some amount of sharpening to try to combat this anti-alias filter that they have to use. So generally, when you buy a camera and it's set to JPEG mode by default, you take a couple photos, you put it on your computer, and it looks reasonably sharp. The reason for that is that this sharpening in camera is combating with this anti-alias filter. But sometimes manufacturers go a little too far with the default sharpening, and it can be over-sharpened. Maybe not to this degree. This is certainly an extreme, but just enough that it doesn't look quite right. So you might need to turn down the sharpening in your camera, or again use RAW in order to be able to apply your own sharpening to the file as you process it. So again, yet another plug for RAW to be able to process something as best as possible. Now, of course, when we're talking about digital artifacts, we also have to talk about lossy compression as well. So artifacts that can result due to compression. And so JPEG is particularly prone to this particular problem. If you save a JPEG file in a very high quality, it's always lossy, but it's not going to lose that much data. You will still retain a lot of the detail that exists within it. But, and we referenced this before when we were talking about file formats, as you compress something very heavily, you will get very strange compression artifacts because it has to throw some data away. So here you can actually see pretty well, I think, the blocking that occurs within JPEG. So you can see that there's these sort of large blocks that just are not visible in this higher quality. And so decreasing the quality in JPEG, which I'm sure most of you know already not to do, but this is really just an extreme example of the compression artifacts that can happen. So using a very low quality, while it will save you some space, will be bad for the quality of your photos. And certainly you should save, I'm sure I've mentioned this, but just to mention it again, if you take photos in RAW, or rather, I'm sorry, if you take photos in JPEG, I recommend as soon as you download them, you make 2 copies. One copy that you're just going to save in its original pristine condition, and another copy that you should feel free to modify however you wish. And if you're very careful about just always using save as, for example, then maybe you don't need to keep 2 copies. But I don't recommend overwriting your original image, because once you've overwritten it with JPEG, you've lost a little bit of data. Nothing like this, but you've lost a little bit of data, you're never going to retrieve it again. So you really should be careful with compression artifacts when resaving JPEG files. So if you do use in-camera JPEG rather than in-camera RAW, I recommend you go into your camera's menu and you set the JPEG setting to the highest quality possible. It will use a little bit more space on your CF card or on your SD card than just the smaller JPEG quality, but you will get the highest quality possible out of it. And usually, the way that camera manufacturers show this to you is usually something like almost literally like this. It's sort of like a quarter circle, and you either see something that's, you know, sort of very jagged or something that's very soft, and you generally want something that looks the higher quality, the smoother version of the quarter circle, and that will be the best way to go. And that's it.